Right, and finally the big theorem, the most important theorem of today's lecture and probably the whole course. So we recall that we have a differential equation that looks like this: y prime equals some function of t and y, where y is the dependent variable and t is the independent variable. And we have our initial value problem. Recall that the right-hand side is supposed to be continuously differentiable. And suppose that the domain of the right-hand side of our differential equation is some d, which is an open set in R2. Alright, so first we assume that our right-hand side of the differential equation is defined in some open rectangle. It means that this open rectangle, when t is, from alpha to beta, let me write it down, when t is from alpha to beta and y is from gamma to delta, this would be a subset of t, subset of the domain. It is more convenient to think in terms of rectangles, because then if we have a rectangle, then t and y are kind of independent from each other. So we can talk about values of t where the solution is defined, and values of y where the right-hand side of the differential equation is defined, right? So further, suppose that, of course, the initial condition is a certain point on the plane ty, and it must belong to the domain. So what we want to say is that this point also belongs to this rectangle, so the point t0, y0 belongs to the rectangle. So then the conclusion of the theorem is that there exists a probably smaller interval. So notice that there is an interval alpha prime beta prime that contains the point t0, but it may be smaller than the interval from alpha to beta. And on this interval, a solution of the differential of the initial value problem exists and is unique. Right? So exists means that there is some function that satisfies the differential equation, and unique means that there is only one such function. So let me demonstrate what I mean. So here is a very complicated differential equation. So here it is not separable. The right hand side contains both y and t, and moreover the right hand side, notice that the domain of the right hand side is non-trivial. So here, because of the division by y, y cannot be 0, and y plus t plus y cannot be 0 either. Right? So, and if y is 0, this is the horizontal, the t-axis, and if t plus y is 0, then this is y equals minus t, so it's this slant line. So that's why these two lines, they are not in the domain, so these are excluded from the domain. So the domain is the rest. Right? So then, but that's the whole domain. The theorem that we just formulated is kind of about restricting. First we need to restrict the domain to some interval, so to some rectangle. So imagine that we have some rectangle that is within the domain. So here is an example of such rectangle. But notice that if you try to just plot a solution of this differential equation that passes through this point, then it would look like this. So in other words, it's not going to be defined for all possible values of t in this rectangle. So its domain itself is going to be smaller. Right? So for example, we can restrict it even further. So it, as this plot shows, that the solution is clearly defined when t is from 1.5 to 2.5. So that's an example. Well, that's kind of a graphical example, just to demonstrate the theorem. I am not going to prove the theorem in the lecture, although it's not very hard. And the reason is because you're going to do it yourselves in tutorial. So you are going to construct the full proof of the Picard-Lindelöf theorem as a series of exercises. I hope it's going to be exciting. So anyway, let me give you a couple of more examples on initial value problems and domains of solutions. So probably the important lesson that we can learn from the Picard-Lindelöf theorem is that the domain of the solution of a nonlinear differential equation could be smaller than the domain of the differential equation itself. Like here, for example. So here, if you look at the right hand side of the differential equation, then because of the division, y cannot be 0, but there is no restriction on t. So the question is, it when we solve it, will there be a restriction on t, or will the domain of the solution be the whole real line? Right? So first of all, since y cannot be 0, so it means that y has to be positive, right? Since the initial value of y is positive, so it means that y has to be positive because it cannot cross the 0 level. So then this is a separable differential equation. So I hope you remember how to solve it. So when you separate the variables and integrate, you get this. So then once this is done, so you need to use the initial condition to solve for c, and then you get that c is 0. But then if you solve for y, it means that y of t is the square root of 8t minus t squared. Well, so let us think a little bit more about this. So 8t minus t squared. So there is a square root. So it means that the expression inside the square root, 8t minus t squared, it has to be non-negative. Otherwise, the square root is undefined. Right? So t times 8 minus t is bigger than or equal to 0. And then if you try to the two zeros of this expression as 0 and 8, 0 and 8, and then t times 8 minus t is going to be probably negative here, positive here, negative here. So hence it is positive on the interval from 0 to 8. And again, since the domain must be an open interval, that's why I am not including 8 and 0 there themselves. A little bit more complicated example. So the idea is the same. There is a division by 0, so it means that y cannot be 0. Here, for instance, y has to be negative, right? Because the initial value of y is negative. So then, when we separate the variables and integrate, we are going to get the left-hand side is a cube, and then we can solve for c using the initial condition. So I hope, I hope you remember how to do it. Anyway, if you don't, try to figure it out yourselves. If you don't get the same answer as I do, then please post a message on the discussion board. So it seems that when you solve for y, then the right hand, we will get a cube root of something, but is it all? And notice that here there is no, since this is a cube root, we don't have this problem of the square root when the expression that we take in the square root of must be non-negative. So cube root does not have this issue. So cube root can be taken of any number, positive or negative. So which means that if we just look at this expression as just something, an abstract function, then its domain would be a whole real line. But notice that y must be negative. It means that 4t to the 4 plus 4t squared minus 8 is going to be negative. And then if you solve this inequality, you will see that the answer is the interval must be from -1 to 1.